Hello everyone, my name is Ria. I am from BSc Chemistry Honors, second year. Today I will be giving my presentation on the topic aldehyde and ketones. Let's start. Aldehyde and ketones constitute two isomeric series of compound, both of which contain the carbonyl group in their molecules and are therefore collectively known as carbonyl compounds. Aldehydes having one hydrogen atom and one alkyl or aryl group linked to the carbonyl group, while ketones have two alkyl or aryl group attached to the carbonyl group as shown below. The aldehyde are said to contain the functional group C double bond OH, simply CHO, and commonly referred to as aldehyde group, while ketones contain the functional group C double bond O, generally termed as ketonic group when present in ketones. Ketones in which the group R and R dash attached to the ketonic group are the same as termed as the simple ketones, and those in which R and R dash represent different group are known as mixed ketones. The presence of carbonyl group in both the aldehyde and ketones is responsible for the close are responsible for the close similarity in their methods of preparation and properties. However, due to the presence of free hydrogen atom in their molecule, aldehyde are more reactive than ketone and also differ from their in certain respects. Now, structure of the carbonyl group. The carbon-oxygen double bond of carbonyl group is composed of a sigma bond and a pi bond. Moreover, in the molecules of aldehyde and ketones, the carbon atom of carbonyl group is also joined to two other atoms by sigma bonds. Thus, the carbonyl group is involved in the formation of three sigma bonds and one pi bond. According to the molecular orbital theory, the carbonyl carbon of aldehydes and ketones make use of three sp2 hybrid orbitals in forming the three sigma bonds. As such, these bonds lie in the same plane with angles of approximately 120 between them. The pi bond between the carbon and oxygen is formed by the sideways overlap over the remaining half-filled p orbital of carbon with a similar orbital of oxygen. The above discussion make it clear that the carbonyl carbon oxygen of two atoms directly attached to the carbonyl carbon lie in one plane. The plane nature of the part of molecule which immediately surrounds the carbonyl carbon is supported by electron diffraction and spectroscopy studies of aldehyde and ketones. Aldehyde, another important aspect of the structure of carbonyl group, arise from the different electronegativities of carbon and oxygen atom. Due to its greater electronegativity, the oxygen atom attracts the electrons of the double bond, particularly the pi electron cloud, strongly towards itself. As a result, the electrons are not equally shared and there is a greater electron density around the oxygen than around the carbonyl atom. In other words, carbonyl group is a polar group, oxygen having a smaller negative charge and carbon having a small positive charge. The polar nature of carbonyl group is probably best indicated by representing it as a resonance hybrid of the following structure. The large dipole moment 2.3 to 2.8 of aldehyde and ketone support the polar character of carbonyl group. Nomenclature of aldehydes. They are named either according to the common or IUPAC system as explained. First, common system. In this system, the aldehyde are named after the acids which they give rise on oxidation. The suffix "ic" acid of the name of the acid replaced by the word aldehyde. The CH3CHO gives acetic acid on oxidation and is therefore named as acetaldehyde. Similarly, from benzoic acid on oxidation is therefore named as benzaldehyde. This system is mainly used for aromatic and simple aliphatic aldehydes. Second is IUPAC names. These names are given in accordance with the general IUPAC rules. The longest chain carrying CHO group is selected. The corresponding word root and the primary suffix ein, in, ein as required are written. This is followed by attacking the suffix al in the place of final e. The positions of substituents, if any, are indicated by suitable numbers, the aldehydic carbon always getting the number 1 because it is a chain terminating group. For this reason, the number of aldehydic carbon is not usually mentioned. It is taken for granted that it must be number 1. For example, the compound is named as 3-methyl butanol. Similarly, the compound is named 4-methyl hex 3-enol. For aldehydes in which the CHO group is attached to a ring, the suffix carbaldehyde is added to the name of the ring. For example, cyclohexane carbaldehyde, benzene carbaldehyde. Ketones. The two systems of naming ketones are as follows. First is common name. Common names of ketones are obtained by adding the word ketone to the name of alkyl or aryl group present in the molecule. These names are mainly used for aromatic and simple aliphatic ketones. For example, CH3COCH2CH3 is named as methyl ethyl ketone. Second is IUPAC names. IUPAC names of ketone carry the suffix "on" and are given according to the usual rules. The longest chain containing the carbonyl group is selected from the name of corresponding hydrogen carbon. The suffix "e" is replaced by "on." The carbon of ketonic group is assigned the minimum possible number along the straight chain of carbon atom and the substituent groups carrying other suitable numbers. For example, CH3COCH3 CHCH3CH3 is named as 3-methyl pentane 2-on. Certain ketones, particularly aromatic ketones, are allowed to retain their common names. For example, acetophenone, benzophenone. Now, formation of aldehyde and ketones. First, we're going to read about the formation of aldehydes. Aldehydes are formed during many chemical reactions. On these, we would describe only those important reactions which are actually used for preparative purpose. First is oxidation of primary alcohol. Aldehydes can be obtained by the oxidation of primary alcohol. However, this method suffers from a serious limitation because the aldehyde formed are further oxidized to carboxylic acid. The oxidation of aldehydes to carboxylic acid generally take place even with milder oxidizing agent than those required for the oxidation of primary alcohols to aldehydes. Therefore, it is difficult to stop the oxidation up to aldehyde stage. This problem can be overcome if the aldehyde formed is removed from the reaction mixture by its distillation as soon as it is formed. It is often possible to do so because the aldehydes have lower boiling points than corresponding to alcohol and they can be distilled away from reaction mixture. For example, 1-propanol having boiling point 370 Kelvin is treated with K2Cr2O7 H2SO4 to give propanol having boiling point 322 Kelvin. As shown above, the oxidizing agent usually employed in the above reaction is a solution of potassium dicarbonate in dilute sulfuric acid. However, if the alcohol has poor solubility in water, a solution of chromic aldehyde CrO3 in water, acetone and sulfuric acid is commonly used. This is known as Jones reagent. Special oxidizing agent. The above method of preparing aldehydes involving the distillation of aldehyde from the reaction mixture as soon as it is formed cannot be used in case of higher aldehydes having high boiling point 373 Kelvin and above. Therefore, some special oxidizing agents have been developed for preparing aldehydes from alcohols. These are first Sarratt's reagent or Collins reagent. It consists of complex formed by careful addition of CrO3 to excess of pyridine C5H5N to give out chromium trioxide pyridine complex. A solution of above complex in methylene dichloride CH2Cl2 oxidizes the primary alcohol to the aldehyde stage, that is RCH2OH, in presence of Cr2O3 dot 2C5H5N and CH2Cl2 gives out RCHO. Second reagent is Corey's reagent. It consists of pyridium chlorochromate PCC formed by mixing chromium trioxide pyridine and HCl. It is also used in methylene dichloride solvent to convert primary alcohol into aldehydes. Third is pyridinium dichromate, which is PDC. It is obtained by mixing pyridine, potassium dichromate, and HCl in CH2Cl2. Next is advantages of oxidation of alcohol with above reagents. As is obvious, advantages of using any of the above three reagent is that they restrict the oxidation of primary alcohol to aldehyde stage. This is because these reagents are used in non-aqueous medium and therefore do not allow the formation of aldehyde hydrates to take place during oxidation. Since aldehydes themselves are not as easily oxidized further as aldehyde hydrates, the reaction stops at the aldehyde stage. In case of oxidation by usual oxidizing agent such as acidic potassium dichromate and Jones reagent, the reaction are carried out in aqueous medium where aldehydes formed are converted into aldehyde hydrates which are readily oxidized to carboxylic acid. Another advantage of using the reagent is that the carbon-carbon double bond, if present in the starting alcohol, are not oxidized. For example, 3-methyl-hex 4-ene-1-ol in presence of PCC gives out 5-methyl-hex 4-1-enol. Now, disadvantages of using above reagents. The use of special reagent discussed above for the oxidation of alcohol leads to the formation of chromium containing waste products which are environmentally very hazardous. At the same time, these reagents are quite expensive and are therefore not frequently used during laboratory oxidation reaction of alcohols. Second method is catalytic dehydrogenation of primary alcohol. The oxidation of primary alcohol to yield aldehydes can also be brought about by passing the alcohol vapors over copper heated to 475 to 575 Kelvin. The process is generally referred to as dehydrogenation as it involves the direct elimination of hydrogen. The dehydrogenation process does not involve the risk of further oxidation of aldehyde formed. Third is reduction of acid chloride, which is Rosenmund reaction. The partial reduction of acid chloride affords another method for the formation of aldehydes. The reaction is usually brought about by passing hydrogen through a hot solution of acetic chloride in xylene in the presence of a suitable catalyst. The catalyst employed in palladium deposited on barium sulfate and the reaction is stopped as soon as the evolution of HCl gas ceases. This helps to prevent further reduction of aldehyde from into alcohol. Nowadays, lithium tritert butoxy aluminium hydride is being used to reduce acid chlorides into aldehydes. An advantage of using this reagent is that it does not affect any other easily reducible groups present in the molecule. Acid chloride used in reaction themselves usually obtained by the action of thionyl chloride or phosphorus halides on carboxylic acids. Fourth, from 1,3-di thiones. The most recent method of the synthesis of aldehyde is by the use of 1,3-dithiones. 1,3-dithiones is an non-aromatic heterocyclic compound containing two sulfur atoms. It can be easily converted into its anion by treatment with alkyl lithium. The anion acts as a strong nucleophile and react with alkyl halide to form alkyl derivatives of 1,3-dithiene. This derivation is hydrolyzed in the presence of Hg2 positive ions to form the aldehyde. The complete sequence of the reaction is shown. Fifth method is catalytic decomposition of carboxylic acids. Aldehydes can also be obtained from carboxylic acid by passing the vapors of a mixture of methanoic acid and another carboxylic acid over manganese oxide at 573 Kelvin. Some other methods which are also be used for the preparation of aldehyde are given below. Sixth method is ozonolysis of alkenes. In this method, the ozonide formed by reaction between alkene and ozone decomposed with a reducing agent to yield aldehyde and ketones. Seventh is Stephen's reaction. Alkyl cyanides on reduction with stannous chloride and hydrochloric acid give rise to the aldimine. The aldimine gets hydrolyzed on warming with water to yield an aldehyde. Eighth method is oxidation of methylbenzene. Aromatic aldehydes can be prepared by the oxidation of methylbenzene by different methods as given below. First, oxidation of methylbenzene to aldehydes is usually carried out with chromium trioxide in acetic anhydride. The gem diacetate initially formed is isolated and hydrolyzed to get the aldehyde. Since the intermediate gem diacetate cannot be oxidized further, there is no chance of the formation of carboxylic acid. Second method is controlled oxidation of methylbenzene to aldehyde can also be carried out with the chromyl chloride or manganese dioxide. The reaction involves chromyl chloride as oxidizing agent is known as Attard's reaction. Third method is it is also possible to convert methylbenzene into aldehydes by free radical halogenation of methylbenzene followed by hydrolysis of gem dihalide. Ninth method is Gattermann-Koch reaction. This reaction constitutes a convenient method of preparing aromatic aldehyde by treating benzene with a mixture of CO and HCl in the presence of a Lewis acid and a copper chloride. In a similar reaction as Gattermann reaction, HCl is used in place of CO. The aldimine initially formed is hydrolyzed to get the corresponding aromatic aldehyde. Tenth method is Ramer-Taimer reaction. It is a convenient method for preparation of phenolic aldehydes, particularly those in which the aldehyde group is present in ortho position to the phenolic group. The reaction is carried out by treating a phenol with chloroform and aqueous solution of hydrochloride solution. Next, formation of ketones. The important method for preparing ketone are as described below. First is oxidation of secondary alcohols. Ketones can be easily prepared by oxidation of secondary alcohol. The oxidation is usually effected by acidified sodium and potassium dichromate, potassium permanganate, or chromium trioxide in a variety of solvents. There is no risk of further oxidation of ketones taking place as ketones are not easily oxidized. Open-or alcohol oxidation. Secondary alcohols can also be oxidized by refluxing with acetone in the presence of aluminium isopropoxide or aluminium tert butoxide. The alcohol taking in oxidized to the corresponding to ketone while acetone is reduced isopropyl alcohol. This process is particularly suitable for oxidation of unsaturated alcohols and is known as open-or alcohol oxidation. Second method is catalytic dehydrogenation of secondary alcohols. Ketones can also be obtained by the dehydrogenation of secondary alcohols by passing their vapors over copper heated at 475 to 575 Kelvin. Third reaction is the reaction of nitriles with Grignard reagent or organolithium compound. Reaction of a nitrile with either a Grignard reagent or an alkyl lithium followed by hydrolysis yield a ketone. Fourth method is reaction of acid chloride with organocadmium compound. Acid chloride react with suitable organocadmium compound to yield ketones. R may be an alkyl or any group, but R dash must be an aryl or primary alkyl group. This is because the organocadmium compound containing only aryl or primary aryl group are sufficiently stable for use.